In this video, we're going to graph cube root functions. And to first get an idea of what a cube root function looks like, we're going to make a table. So we have f of x equals the cube root of x. We're going to use the following table to see what these graphs look like. And I picked some numbers here, and you'll see why I picked these here in just a minute, that these are perfect cubed numbers. So I can take this -8, and I can go to my calculator and try to type in the cube root of -8. What you will get back in your calculator screen is -2. Do that for -1, the cube root of -1, or in other words, what number times itself 3 times gives you -1. That will give us the value of -1 again. What's the cube root of 0? That would be 0. The cube root of 1 is 1. And the cube root of 8, which is 2, because 2 times 2 times 2 is 8. And I can take all of these values and I can go to my graph over here to the right and I can plot the points. I have a dot at -8, -2. I have a dot at -1, -1, 0, 0, 1, 1, and at 8, 2. What I typically do when I graph a cube root function is I start at the middle point at 0, 0, and I curve it up to the right, and then I go back to the 0, 0 point, curve it down to the left. That 0, 0 point has a nice name for itself, and we'll talk about that here in just a second. But here we got the cube root of this, of x, and we need to talk about what's the domain and the range of the cube root, because in the square root, there was restrictions on the domain and the range. Is it the same for the cube root? Well, domain, let's look at the x-axis. If you notice, if I go left and right, with the arrows going on forever left and the arrows going on forever right, no matter where I look, above, below, or on the x-axis, I will always run into a point somewhere. So the domain is not like it is with the square root of x. Here we have all real numbers. So you can plug any number you want into the cube root. Is it the same for the range? Look at the y-axis. I look to the left. I can look to the right. I can look on the y-axis. No matter where I go, I can eventually run into a dot. Now, I know to the left here, it doesn't seem like there's many dots that I can look at, but what gives away that we will run into one of those is that the arrow, this goes on forever. It does eventually go down far enough that I can find an ordered pair. And the same thing is true for the right side of this. So the range is also all real numbers. And we like this because that means you can plug in whatever you want. Answers you can get back potentially anything. Okay, going back to that 0, 0 point. That is called the inflection point. And what an inflection point is, it's the point in the graph where it changes its curvature. So on the bottom left, it was curving going down to the left, but then it changed its curve going up to the right. Okay. So how do we use some of this information to graph? We need to know some key characteristics about the transformation form of a cube root function. The first thing is, how do we find the inflection point? Well, we can identify the inflection point within the function by doing the following ordered pair. What's the opposite of the h number that's in the function, comma, the k number, the vertical movement? The next thing we need to know is, what would be the end behavior? The good thing about the cube root function is that there's only 2 types of graphs that you can get. And you can find that by looking at the a. What's the number or the value of the number in front of the cube root? If that a happens to be positive, the arrows will go down to the left, up to the right, similar to a positive slope. If the a happens to be negative, then it will go up on the left side, down on the right side, similar to a negative slope. And once you do this, we'll plot the inflection point, figure out where our arrows are going to go for the end behavior, and then we need to get really good at these types of movements. This correlates back to that table I made at the very beginning of the video. Being able to go from the inflection point, going right 1, up 1, then going back to the inflection point, going right 8, up 2, go back to the inflection point, go left 1, down 1, once again go back to the inflection point, go left 8, down 2. Okay, and those movements could change dependent upon what kind of number I have in front of the cube root. So let's put all this in action. Let's graph the following functions here. The function we have first What's the cubed root of x plus 3 minus 4? What would that look like? Well, if we think about some of the characteristics that I talked about, what was our inflection point? It's the opposite of the h number, so it's plus 3 in the equation. That means it'll be negative 3 in the inflection point, and then negative 4 on the outside will be the y value of this. Next, what is the end behavior? Well, we need to see what's the sign in front of the cube root. There's no negative there, which means it's positive. So that forces the end behavior to go down on the left side, up on the right side. That's pretty much all we need to know to graph this. So we go to our graph paper, plot the inflection point, and then I can go from that inflection point, right one, up one, go back to the inflection point, go right 8, and then up 2. And whatever you're going to go right and up will be the same exact thing going left and down on the other side of that inflection point. So go left 1, down 1, go back to the inflection point, go left 8, down 2, and I've got enough dots to draw this cube root function. So draw the arrow from the inflection point up, go back to the inflection point, draw my arrow going down, and there is what the cube root of x plus 3 minus 4 will look like. Another function. How about y equals negative 2 times the cube root of x minus 1 plus 3? What's our inflection point? We find the inflection point by looking underneath the root and the outside of the root. The x value is always opposite of what's underneath the root, so 1 comma 3. What's the end behavior? Well, this time the a is negative because of the negative 2, which flips the arrow. So here's what our end behavior will look like. It's going to go up on the left side, down on the right side. We will also do some multiplication with that 2, but we'll go ahead and start graphing here. So go to 1 comma 3, we plot our dot, and from here, our normal movement would be to go right 1, up 1, and put a dot. Now that vertical movement that I just said by going up 1, I'm going to multiply it by negative 2. So 1 times negative 2 is negative 2, which that product tells you where we're going to move. So instead of going right 1, up 1, we're now going to go right 1, down 2, because 1 times negative 2 is negative 2. Our next movement from the inflection point typically is right 8, up 2. But that movement of up 2 gets multiplied once again by negative 2. 2 times negative 2 is negative 4. So it forces me to go right 8, down 4 steps. And then, from here, whatever I went right 1 and down, I would do the opposite to the left side. Go left 1, up 2, go back to the inflection point, go left 8, up 4. Got enough dots to draw the picture of this graph. So I curve it up to the left, curve it down to the right, and there's what negative 2 times the cube root of x minus 1 plus 3 will look like. I got one more example for you. What about 1/2 times the cube root of x plus 2? Here you may notice that there's not a number underneath the cube root with this. So another way that you could think of this is, what if you just add a 0 into there? 1/2 times the cube root of x plus 0 plus 2. This will help us find that inflection point. So the inflection point will be 0 comma 2. What's the end behavior? The 1/2 is a positive value, so that tells us that the end behavior will go down on the left and up to the right. And again, we got all the information we need to graph this function. We have a graph, plot our inflection point at 0, 2. Typically, again, we would go right 1, up 1 to start. But 1 times the half that we have here, half of 1 is a half. So I'll now go right 1, up a half a step. Typically we go back to the inflection point and go right 8, up 2, but half of 2 is 1. So now I'll go right 8, up 1. Since I went right 1, up a half, right 8, and up 1 full step, we'll do the opposite of that to the left by going left 1, down a half a step, and then left 8, down a whole step, and that compressed the graph a little bit. So there's my arrows, and once again, there's what 1/2 times the cube root of x plus 2 will look like. And that is graphing cube root functions.